All right, welcome back. Let's talk now about normal distributions and their applications. So if you remember, the normal distribution was the one where everything was nicely centered around the middle point. Okay, there really was no skew to the right or to the left. Well, there's a special case of the normal distribution where the normal random variable has a mean mu equal to 0 and a standard deviation or sigma equal to 1. Okay, in this case, the mean is equal to the median, which is equal to the mode. Exactly 50% of the values lie above the mean. So everything over here is 50%. And everything on this side is also 50%. Okay, the normal random variable is called a z-score. We're going to talk more about the z-score in just a moment. So this is what the standard normal distribution looks like. The mean, again, or the average is equal to 0, and then the standard deviation is equal to 1. The z-score, which is over here, is a representation of the standard deviation. Okay? It indicates how much a given value differs from the mean. It's the number of standard deviations a given point lies above or below the mean. So we can take any data that we collect and we can standardize it using a standardizing equation, which is over here. So we can easily find areas under the curve associated with different values. Again, I just want to point out that you will take a course on this topic, and so it's okay if you don't understand everything. I just want you to get away the basic meaning of what it is to standardize data so that we can use this curve to easily get values for under the curve. Let's think about how we could apply this to the device that we've been working on. Okay. The question is, what's the chance that when we aim and fire, we will hit our goal or our scoring structure? Well, first we're going to need a bunch of data. If we were actually able to finish this project, you would have been able to collect those data. But you would launch, measure, record, and then repeat. And then we could think about how repeatable your ball's flight is. Now, wind in the room, variations in how the trigger is released, the exact diameter and center of gravity of the ball you're using, these all make slight changes to the trajectory of your ping pong ball in flight. If you took lots of samples of distance, each of your data points would have a slightly different value. One way to look at the data, again, is to create a histogram, which now you know how to do in Excel. If you wanted to try to use MATLAB, you could use this following information to help you do that. So why do the data vary? Okay, this gets us into a topic of errors. There are two types of errors that we're going to look at, systematic and random. Okay, systematic errors are an offset or error in the data that always happens in a certain way. An example would be that your measurement instrument is out of calibration and reading low, or when you thought you were applying a given force, but you were actually applying more or less. Okay, those would give you systematic error. You can see in this picture down here at the bottom, we have all of our points over here in one general area. Random error is unpredictable variations. Examples include electronic noise in an electrical instrument circuit, or a solar collector having irregular changes in heat loss rate due to changes in the wind. This is the kind of error that averaging can really help. So if you look over here in the picture for random error, you can see that they're just kind of all over the place. And if you were to average them, then it would really help deal with that error. A normal distribution has only random error. So let's think about what the probability is that you are getting your ping pong ball inside the goal. So once again, if we were actually able to finish this project, you could collect data to see how accurate your launch was. You could actually record how far each landing is from the ideal spot. And then we could take the following steps to analyze the data. Number one, measure the distance from the ideal spot to the actual landing spot. You would do that many, many times. Then we could find the average and the standard deviation on the ball's path. We could calculate a z-score or z-scores, find the area under the curve, convert that to a percentage, and then make conclusions. So let's go back and look at the DART data that we worked with for the histogram. They've already collected data for us, and so we have that here. Now, this time I'm going to look at the horizontal distance, so how far off horizontally our DART was each time from the bullseye. Then the next step is we can calculate the mean and standard deviation for those data. In Excel, again, you just type out average, and then you'd put in all of these values, and then for the standard deviation, you would use the function stdev.p, and again, using these same data points. Okay, so now I have my average and standard deviation on the DART's path, 0.397 inches and 1.207 inches. The next step is to find the z-scores. First off, we need to point out that the radius of the bullseye is 1.75 inches. Okay, you would know, obviously, the radius of your target in your scoring structure. In our case, with the DART, it's very thin, so we don't have to take its dimensions into account, or we're just going to ignore those dimensions. But if you're doing it for your ping pong ball, then you would need to take the size of your ping pong ball into consideration. The z-score is for a particular value. So in our case, we're going to think about getting plus or minus 1.75 inches from the center. Okay, so we think of this red cross down here as our center. We would have plus 1.75 to get us over here, and minus 1.75 to get us over here. Those are the outer edges of our target. So as long as we hit anywhere in that area, then we are counting it as success. So we need to find two z-scores, one for negative 1.75 inches and one for positive 1.75 inches. We take this equation, z is equal to x minus x bar, which is our average or mean, divided by s, which is our standard deviation. And then we can plug in the values to get a negative z and a positive z. Okay, and then we can put those onto our normal distribution and calculate or get the associated areas. So our negative z is the value we're going to test is negative 1.75. We're going to subtract the average, which is 0.397, and divide by 1.207, and we end up with negative z is equal to negative 1.779. Then for our positive z, we just take a positive 1.75, subtract the average, divide by the standard deviation, and we end up with a z value of 1.121. The next step is we want to find the area. Okay, so we have a negative z value. What was it? It was negative 1.779. And then our positive z value was 1.12. Okay, there are various ways that we can figure out what the probability or what the area under the curve is. Okay, we can actually go to tables. All stats textbooks have tables that you can look at to get the area. Note that those values are cumulative. So we have the negative z, which gives us this area here. But if we look at the positive z, we're getting this cumulative area. Okay, so just keep that in mind. You can also use Excel or MATLAB to get those values. I went and used this handy website here and got the area for the values of 1.12, which was 0.8686. That's all this area here. And then the value for negative 1.778 is 0.0377, which is this area here. So if I take this f of z and subtract f of negative z, which is here. So if I take that and subtract that, then I will get this area here in the middle, okay, which is 0.8309. So what exactly does the area mean? Okay, I've got a standard normal distribution up on the screen, and these outlines here where I'm drawing in red that correlate with the negative z and positive z, that's where we barely miss the bullseye circle. Okay, so we just barely miss if we hit it on that line. This area here in the middle, let me change colors, is equal to 0.8309. And basically that means 83.09% of the time we're good. Okay, our dart hits the area of the bullseye. Then the yellow areas, so here on the left associated with the negative z, we have an area of 0.0377. So 3.77% of the time we will be off the target to the left. And then over here on the right-hand side, our area is 0.1314, and 13.14% of the time we will be off the target to the right. So as good engineers, we always need to ask ourselves, do those numbers make sense? The results showed there was a higher probability of missing the target to the right than to the left, 13% versus roughly 4%. So let's look at the histogram for this is the histogram based on the horizontal distances. And let's see if that makes sense. So even if we don't go into a great analysis of this histogram, our results do make sense because we can see that there are 5 darts from 0 to -2 that fell into that area versus 10 darts that fell into the bins from 0 to greater than 2. Okay, so that makes sense. It makes sense there are more darts that are too far to the right versus roughly 4% too far to the left. And basically how could we use that data to determine what changes we could make to get our data more to the center? Well, we would also need to analyze our vertical data. But basically, it could tell us that if we change the angle slightly and adjust it more to the left, then we would have more of our more of our darts hitting here in the middle. Okay, so you could do a similar analysis with your ping pong ball launcher. There are 2 assignments for this for week 11. The first one was to create a histogram, which I already went over, and there is also a quiz that you need to complete, and it just tells us that you got most of the information from these online videos. If you have any questions at all, please feel free to contact me. My email address is on the screen. It's just jennifer.lovely@uky.edu. Thank you all, and I hope you have a good rest of your day, and I hope that you're staying sane despite not being able to be on campus with all of your friends. Hope everybody's doing well.